most severely? When they get further apart or when they get closer together? And that's all Coulomb's law is saying. Is like, look, the force will increase the closer they get to one another. And this is true for the ions too. Okay? A +1 ion and a -1 ion are going to feel more strongly attracted to one another when they're this far apart, as opposed to, when they're separated by a greater distance. So this is something that you're already kind of familiar with on a qualitative sense. Okay? It should be something that's not too difficult. Coulomb's law is something that we're going to be coming back to again and again. If we look at Coulomb's law in terms of how it relates to the atom, what are my charged particles? Because we're not dealing with ions, so what are my charged particles? Well, we have two things. One thing we have to consider is the charge of the electron, the other is the charge of the nucleus. Now, Q1, that's the charge of your electron. And if Q2, the charge of the nucleus, normally would be good enough, however, it's not sufficient. It's not just simply the charge of the nucleus we have to look at. And I'll explain to you what I mean by that. I find that if you do this pictorially, it's helpful. So you're going to see me do the following as I go through. I'm going to be going ahead and we'll look at just nuclear charge to start off with. The charge of the nucleus. What determines how positively charged the nucleus is? Matthew? Number of protons. So, and we know that Z represents the atomic number, which is the number of protons. So when we talk about nuclear charge, we're really talking about Z. And there's a trend. As you go across, and I like to do this pictorially like this, it's easier to memorize that than a couple of sentences. So, and it'll make it easier to see patterns among some of the trends that we're looking at. You can see which ones do the same thing, and that helps to also, commit this to memory. As I go across a period, what's happening to my nuclear charge? Maria? Mm-hmm. Yeah, the nuclear charge is getting, so how do you know that? There you go. You can see a steady increase in atomic number. That means more protons in the nucleus, so the nucleus is more positively charged. So we're going from low to high. What about going down a group? Lance? As I go down a group, yes, it's going to go again from low to high. Everybody okay with that? All right. The problem is we have to also consider the distance the electrons are, but we also have to consider some other effect known as shielding effect. It turns out that inner electrons help to shield the nucleus. I really, 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 really hate the phrase shielding effect. It's a real misnomer because it suggests that those inner electrons, let me show you what I'm talking about. The story goes, or the statement goes like this, is that if you have electrons that lie between the nucleus and say your valence electron, so there's your valence electron. The shielding effect says that these electrons shield the valence electron from the pull of the nucleus, and so the pull the nucleus has on this electron is actually a little bit less than what you would expect thanks to these inner electrons. You guys with me? All right. That's just wrong. That's just a wrong way of looking at it. And I'll explain to you. Look, I told you that I had 3 younger sisters. I didn't tell you that we were hellions when we were younger. I mean, I'm talking about little kids. We had a knack for like getting into trouble. You could always tell that when we had sort of pushed a little too far, the babysitter or my mother, they'd start to get that twitch, and you knew that hell was going to be raining down upon you. I found at an early age, if I could situate my sisters from the rampaging babysitter in front of me, that effectively shielded me and allowed me to escape. Now that is the shielding effect, okay? Where you have this, by the way, it only works if they're right in front of me. If my sisters were a little bit in front, but to either side, yeah, that wasn't very effective at all. Okay, it's much better. So if they're right here, that's no good. They had to be up front. And there's an analogy that actual shielding. That's not what's going on here. Okay? It's not like somehow these electrons are blocking the positive charge that this electron can experience. It's not what's going on at all. What it really is, what shielding effect really is the repulsion. These electrons are negatively charged, and so they're repelling this outer valence electron. The nucleus is pulling in on it, but the hold the nucleus has on it is not going to be as good because it has to contend with that extra repulsion of those inner electrons. So shielding effect is a little bit, shielding effect suggests that they're like my sisters, they're blocking the nucleus's ability to grab hold. That's not what's happening. They're not blocking anything as far as the attraction between the valence electron and the nucleus. What they are doing is adding a new twist to the equation. They're adding repulsion, which helps to counteract the attractive force of the nucleus for the electron. Does that make sense, guys? So shielding effect really is a reduction in the hold the nucleus has. Shielding effect is a reduction on the hold a nucleus has due to electron-electron repulsion among the inner electrons for the valence electrons. Again, it's a reduction in the hold. Shielding effect is a reduction in the hold the nucleuses have on a valence electron due to electron-electron repulsion between the valence electron and underlying inner electrons. Electrons, for instance, belonging to the same energy level do not effectively shield one another. So, for instance, a 2p electron and a 2s electron, 2s electrons do not effectively shield 2p electrons. The 1s electrons, on the other hand, yeah, they effectively shield any electron in the second energy level. Now, if we take the shielding effect into account along with the nuclear charge, so let's talk about shielding effect first of all. What's going to be the trend in shielding effect? As I go across a period, what's going to happen to my shielding effect? Joe? The fact is, guys, there's going to be really no marked change. I'm not saying that there's not a little bit of an increase, but there's really not much in the way of a marked change. Why is that? Okay, well, let's take it the other way around. What's going to happen to shielding effect as I go down a group? Well, pardon me? Well, right. So we said, here, let me draw it this way. Let's suppose I have my positively charged nucleus, and I have a couple of electrons, and these electrons are at a lower energy level shielding this electron, right? All right. If I go ahead and bring in and compare the difference, this electron, do you think it's experiencing greater shielding? Because you have a full another energy level separating it. In other words, as I go down a group, what's happening to my outermost energy level, Alexa? Well, what am I doing with it? What's happening to the outer energy level? What's the outer energy level for sodium?
Okay.
Outermost energy level. That is not an energy level.
3.
That's a 3, the third energy. What's the outermost energy level for potassium?
4.
What is it for cesium?
6.
So what's happening to the outer energy level as I go down?
It's getting further.
Because it's getting greater. In other words, as you go down a group, and this is the point you need to understand, as you go down a group, you're adding energy levels, which means that you're adding you're adding a whole new layer of shielding electrons. So as you go down a group, shielding effect is going to go from low to high. You guys with me? Make sense so far? Remember, you really can't increase, Alexa, you really can't increase shielding anyway unless you're adding energy levels worth of electrons. If you're just simply going to add them to the same energy level, that's like putting my sisters like this. It's just not going to help. But now you have two sisters there. Yeah, and the babysitter's, it's just not going to help. Okay? I mean, in terms of the analogy I was trying to use to help see, you really need them out between. Okay? And the only way to get that is to have energy levels lower than you're the one that your electron's in. If I go across, what's happening to my outermost energy level, Alexa, as I go across?
Well, when you're in D.
No. What is happening to what's the outermost energy level for vanadium?
4.3. No, it's 4.
What's the outermost energy level for gallium?
4.
What's the outermost energy level for all the elements in row 4? Okay, so what's happening to your outermost energy level as you go across a period? Nothing. It's not changing. Which means since you're not adding as you go across a period, since you're dealing with the same darn energy level, you're going to see no marked change. Now, again, you can write this down, guys, but it's more important, or just, I should say, is just as important, that you understand it. In other words, if you memorize shielding effect goes from low to high and across, there's no marked change. And I ask you, well, why is that? Can you explain that? Because, Ada wasn't here and all of a sudden his phone ran out of battery, so she needs someone to teach her. Would you be able to explain it to her? Okay, it has to make some sense, in other words. Questions?
Couldn't it decrease if you increase the number of valence electrons as you go across the row?
Couldn't it go ahead?
If there's more valence electrons counteracting the negative charges of the other electrons, there wouldn't be as much
It's not to say that there isn't some kind of increase. Remember, it's for the valence electrons now. Okay? Part of this has to do with, for instance, if that's my nucleus, any electrons that tend to stick around the nucleus are going to be better at effectively shielding electrons than electrons, let's say, that might, you know how the d orbitals look like this? Okay, actually, it's more like that. Because the lobes are extended out like this, d orbital's not very good at shielding. That's because the electrons spend more time away from the nucleus than they do around the nucleus. Does that make sense? You with me so far? All right. Going across a period, you're going to end up seeing a slight increase in shielding, but it's just that. It's slight. That's what I mean when I say no marked change. It's just not worth mentioning. And it's because they just don't really add a heck of a lot. If you want to have any real serious shielding, you need electrons further down in a lower energy level.
I thought there would be like a slight decrease.
Oh, no. No, if anything, there would be an electron, for instance, 1 gallium. Okay, so gallium. This ends in 4p1. All right. Well, you got 4 s electrons that can shield it. Well, and s electrons are good. I mean, s electrons are spherically around. I mean, so s electrons are the best at shielding of all the elements. Of all the orbitals, s electrons are the best. But 4s versus 4p, they share so much common space. It's just not going to make a big a deal. Okay, it is going to be a slight increase, just not enough to comment upon. Everybody with me so far? All right. Now, here's where we put everything together. If we consider what's happening to the nuclear charge, and we consider what's happening to the shielding effect, we can now define what's happening to effective nuclear charge. Z star, also sometimes written as Z sub EFF, is effective nuclear charge. I think, let me double check this, guys. Yeah, I gotta do something about this. All right, look, on your worksheet, I wrote effective nuclear charge on your worksheet as ENC. No one calls it that. Okay, I call it that, I should redo, and I need to